Okay, what we have talked about in Hilbert's Grand Hotel, now we are going to give it a more rigorous foundation. And to do that, actually, we're going to discuss the cardinality of the Cartesian product of the set of naturals with itself. And because this corresponds to the let's say, infinitely many buses in the ferry and infinitely many seats in each of the buses. So essentially, you can define each of your newly arriving customer as an order pair, and the first number here is going to refer to the let's say the bus number. Let's say bus number, and it's a natural number. Okay, it goes to infinity, and the second component may be referred to the seat number inside the bus. Okay, so here you see the Cartesian product of natural numbers with itself is going to be the entire set of your new customers in that scenario. Now, let's see how this is a countably infinite function. Essentially, that is based on a concept called pairing functions. A pairing function is, by definition, is a bijection from this Cartesian product to set of natural numbers. Now, we are going to actually see this on this picture where we have all the ordered pairs, um, let's say, tabulated here, and the rows here correspond to the first number in the ordered pairs, and the column headings correspond to the second component. And define this procedure where you start from the number 00, and then you go to 10 and then 01. So essentially this was where the sum of the components is 0, and this is the line where the sum of the components is 1, and then you move on to from 01, you move on to 20, and you will move along this line of where the sum of the components makes 2, 2011, and then 02, and then you come back to 30, and now you are in the line, let's say, where the sum of the components is 3, 30, 21, 12, 03, etc. So you move on like this. Then you come down to 40, then 31, 22, 13, 04, and then 50, and then 41, 32, 23, 14, and then 05, and then all the way down to 60, etc. This is the enumeration. This is an order, as I said. If you can come up with a unique order that is definable as a function, then that is going to be countable. So this procedure is called Cantor pairing function. Okay, so the German mathematician Georg Cantor came up with this idea, and he is actually seen as the father of modern set theory. Has a lot of results regarding infinite sets and uh, axiomatic set theory, etc. But in this context, the Cantor pairing function gives us, or is denoted in this way. The input is, of course, an ordered pair because the domain is the Cartesian product, and the output is a natural number. And the statement, the expression is here. K1, K2 is the ordered pair, and if you apply this, you are going to get a natural number. And naturally, this being a bijection, it is invertible. I'm not going to give the procedure to do it here, but you can look it up. It's not that difficult. So the idea here is, for instance, if you ask me, let's say, 243rd ordered pair. What is the 243rd ordered pair? It is possible to find that ordered pair, and vice versa. So this gives you a bijection, which means the set of the Cartesian product of naturals with itself is also countably infinite. Okay, so it looks like you increase it with one dimension, but it's not even bigger, right? So this increases by one dimension now, but it's not a bigger set. It has the same cardinality with set of natural numbers. So uh, uh, moreover, you can also generalize this procedure, and you will see that uh, any power where k is a positive integer of set of natural numbers is countably infinite, and you can say that this is Aleph now. Okay, so what about set of rational numbers? We have talked about set of naturals and the Cartesian product of set of naturals with itself. So what about the next seemingly bigger set of rational numbers? Remember the definition of set of rational numbers is the set where we can define as the set of the numbers in the form of m divided by n, where m and n are integers, and of course n is non-zero. So essentially this is integer ratios. Well, here in this picture we only have positive rational numbers, but we have just seen that if you double it, if you just like make a copy of each element, and that's going to be the case here. If you have 1, you will have -1. If you have 1 over 2, you will have negative 1 over 2. If you have 2 over 5, you will have negative 2 over 5. So we'll just focus on the positive ones, and it will have the same cardinality. And this looks a lot like the ordered pairs from earlier, because you just have a pair of a pair of integers, and a rational number is just their ratio. Okay, so it already looks like this is going to be countable. But can we come up with a pairing function, let's say? Now here, this is a little bit different because there are repeated entries. Let's say you start with 1 over 1, okay? And here, I'm not going to do the Cantor's order. It's a little bit different. This is like a snake moving along this table. But this is also widely used approach to such sets. Now from 1, 1, you can move to, let's say, 2 over 1, and then 1 over 2, and then towards right 1 over 3, and then the natural next item would be 2 over 2, but see, 2 over 2 is the same as 1 over 1, so I have already covered this number. So it actually doesn't exist anymore. It has no place in this table. So I can directly move to 3 over 1, and then 4 over 1, and then 3 over 2, then 2 over 3, then 1 over 4, and then 1 over 5, and then naturally it would have been 2 over 4, which was already covered by 1 over 2, and then 3 over 3. Again, it's the same with 1 over 1, and then 4 over 2, and this is the same with 2 over 1, so they are all out. So I directly move to 5 over 1, and then 6 over 1, and then 5 over 2, and then 4 over 3, and so on. So this procedure is a little bit, of course, more difficult to write an analytical expression for the pairing function, but what suffices is a list. So 1, 2, 1/2, 1 over 3, etc. Whatever the expression is, you can actually come up with such a list, and it is possible to actually produce any rational number with a corresponding natural number. And this shows that, well, at least it shows that the set of positive rational numbers is countably infinite, but you can generalize this to set of all rational numbers, and that is countably infinite also.